And welcome back, Calculus. We're going to take notes on related rates, section 3, triangles. Per the poll I sent out, where I had double-digit people answering the polls, we have Mr. Cheney here. Mr. Cheney, good morning.
What up, Calculus?
All right, today we're going to look at related rates 3, triangles. The objective is to solve related rate problems using the Pythagorean theorem in similar triangles. So it's going to be more on what we've been doing in the past, but we're going to now use things like Pythagorean theorem and similar triangles to answer the questions about that. All right, so these are the two formulas we're going to use to relate sides of a triangle.
Oh, I know Pythagoras.
What do you know about Pythagoras?
Well, I was just going to ask you what you know about Pythagoras.
Well, I watched a video about him he was a member of the Pythagoreans. He came up with...
What, are you saying he named a group after himself?
No, he was a member of this kind of cult of mathematicians.
Called the Pythagoreans.
Yes.
But he's Pythagoras. He named the cult after himself.
This is thousands of years ago.
We're supposed to look up to this guy?
There's a lot of it. Well, his whole cult ended up, from the stories that I've heard, hunting him down. He came up with a number that was not what's called an irrational number, a number that kind of like doesn't fit like the whole numbers and the fractions.
Okay. And
the Pythagorean theorem is kind of what gave birth to these what are called irrational numbers, and they were not happy about it, and so they hunted him down for that.
Flo knows his history.
The thing about it's so long ago that no one knows really what happened. And this is just one story that I've heard that I choose to believe.
This is the truth. This is why I don't teach ancient history, all the modern stuff.
Yeah.
Where they wrote this stuff down.
Yeah, a part of the story that I heard is he was afraid of beans. And as he was running away from people, there was a beans field, and he refused to run into the beans field. And so because he tried to go around the field, that's how they ended up catching him.
Zero chance this is a true story.
Correct.
Okay.
But there actually is Pythagoras' cave where he kind of discovered this theorem is somewhere in Greece.
Nice.
Mr. Ash was telling me about it. So if I were to do like one of those ed trips, that's in my repertoire.
He's the man.
Yeah. So this is one way to relate sides of a triangle. If we have legs A, B, and C, and it's a right triangle, then they must be related to each other by the Pythagorean theorem. And then if we have two triangles kind of like nested inside of each other, we have similar triangles. So whatever the side lengths are, if we have the heights are A and B, and maybe the bases are C and D, then the ratio from A to B is going to be the same as the ratio from C to D. So these are just ways of relating variables to each other so that we can do our related rates part of the problem. Real quick, I did write this. Have you ever heard of a 3-4-5 triangle?
No.
So a 3-4-5 triangle is kind of like the most basic. If you're ever doing like an SAT or something, they'll often use 3-4-5 to make a right triangle here. 3-4-5 fulfill the Pythagorean theorem. If I use A, B, and C to
I
be,
see it. So if 3 is A squared would be 9.
Yep.
Plus 4 squared would be plus 16, that's 25.
Right.
And that equals our 5 squared, 25.
Correct. So these are three numbers that fulfill the Pythagorean theorem, and they're actually called a Pythagorean triple.
Is that a key term?
This is just kind of like a cheat code to do something quick later. We don't necessarily need to know this, but just kind of like a fun little math thing. If you have three positive integers that fulfill the Pythagorean theorem, that's what we call a Pythagorean triple. So three positive integers. Integers are just whole numbers. When we say whole numbers, those are positive. When we say integers, we can say positive or negative. But then using the phrase positive integers, I'm really just talking about whole numbers.
That's rational.
Yeah, three positive integers that satisfy the Pythagorean theorem. So, although 3-4-5 is like the most basic one, and very often on an SAT, if you see a triangle side lengths 3 and 4, without doing the Pythagorean theorem, you know the other side's going to be 5 if it's a right triangle. Mm-hmm. But if I double those sides, 6, 8, and 10, that'll also be the side lengths of a right triangle. If you have 6, 8, and 10 of, three pieces of wood of those sides, they have to make a right triangle when you put them together.
36, 64 equals 100.
Right.
All right.
So, yeah, and you can, if I tripled all these, 9.
So that'll work forever.
12, 25, right. So there's an infinite amount of Pythagorean triples you can come out of the 3, 4, 5. And that's not the only, like, prime Pythagorean triple. There's other other ones that are not multiples of 3, 4, 5 that exist. And
It's the most basic one that we can do.
yeah, this is a very common one.
Cool.
So in this case, if you recognize you have like a side length of 3 and 12, you might know without having to do the Pythagorean theorem that the last one's 25. Because this is 3 times 3, this is 3 times 4, and that's 3, excuse me. That one's not 25. That's 15. 3 times 4 and 3 times 5. So it's just kind of sometimes if you recognize these numbers, you might not have to do the Pythagorean theorem to find the third one if you know, if you recognize it.
Okay.
So here's the first example. Mr. Cheney, if you would like to read it, please.
Yeah, okay. Let's see. Jasmine is, like Princess Jasmine?
Yeah.
From Aladdin?
Yeah.
Is going east on Alamo. I don't remember an Alamo Street in Agrabah. Did I miss that in the movie?
Must have missed it in the movie.
Those were nice streets. I think Jafar gets a bad rap in Aladdin. I think he managed Agrabah really well as like a kind of like a chief of staff situation. Like he shouldn't be king. Goes without saying.
Sure.
But just a guy that he can execute policy. I think he was actually really good at that.
He did seem to be well educated in the affairs of the town, of the city.
Right. He was efficient. Right. So, I don't know if there was an Alamo Street there, but I will tell you that the streets of Agrabah looked fine. There were shops. There was commerce. Right. There was an economy happening. I think we need to reevaluate Jafar's reputation.
I'd be interested to see another take on that.
You know how
kind of like Wicked,
Wicked, Cobra Kai, right?
Yeah.
When Johnny Lawrence we could go back there, I think, and make it seem like he's the good guy, and this riffraff Aladdin comes in and just messes up everything. The chaos that's thrown into that kingdom because of Aladdin's changes.
Right off the bat, he was stealing bread.
He's a thief, and he's the hero? Please. Anyway, Jasmine is going east on Alamo Street at 40 feet per second and is 200 feet from the intersection. Meanwhile, Theodore Roosevelt, am I right?
Potentially.
All right, Ms. Virtue would love that. Meanwhile, Theodore is going south on Heights Street at 30 feet per second and is 600 feet from the intersection. Princess Jasmine wishes to determine at what rate the straight line distance between them is changing.
Excellent. Interesting thing enough, for whatever reason, I've named all of my cars after Disney princesses.
All of your cars plural? What do you got, a garage of cars?
Well, like in my life, I've had, I think, 2 or 3.
Okay, across your lifetime.
Right.
You don't own like 5 cars.
Correct.
Right
I own 1 car.
And you name them after
but
what?
One of my first car had that kind of like bluish, I don't know, like that jasmine blue color. I don't know what.
Oh, Jasmine Blue.
I don't know if that's actually what it's
fine,
called.
I get that.
But I named my first car Jasmine.
That's beautiful.
After Jasmine. She was my favorite in my youth. All right. So in this problem here, we know Theodore is going down High Street at 30 feet per second. We know Jasmine's going down Alamo Street at 40 feet per second. We're trying to find out what is the rate of change of the straight line distance between them. I want to make a straight line here.
So as Theodore is moving south, Jasmine's moving east?
Correct.
Okay.
So I always recommend when we're doing these problems, first try to draw it out, label what you have, and then try to find out in calculus terms what you're looking for. So we know Jasmine is 200 feet from the intersection. So this length right here is 200 feet. At that same point in time, Theodore is 600 feet from the intersection. And we're asked what is the rate of change of the straight line distance. So I'm going to label these sides instead of A and B and C. I do like to use C as the hypotenuse. I tend to use X and Y instead of A and B, and it's not to confuse people. It's because whenever I'm seeing a triangle and I see X, I'm thinking horizontal distance.
Well, also like the axis, right?
Right.
So, like if this were a graph, you'd have the X and the Y.
Exactly. Okay. So in my mind, when I see X, I know it's horizontal and Y is vertical, and then it kind of changes up a little bit. So we not only do we know X and Y, but we also know the rate of change. So the notation we use for the rate of change, I've been saying dx dt, but an easier way is doing this little x prime. Okay. So that is the rate of change. And Jasmine's rate of change is 40 feet per second. We got Theodore's rate of change, so I'm going to call that y prime. That's the vertical distance. Now, it's 30 feet per second, but the distance between him and the intersection is decreasing. Mm-hmm. So it's actually going to be negative 30 feet per second. And we're trying to find out the rate of change, the straight line distance rate of change. So I really want to know how this line is changing. So that's what I'm looking for. So given this information, I need a relationship between x, y, and c. And if I have a right triangle here, the Pythagorean theorem is what relates the three variables to each other. So here's my relationship between those variables. And all these are changing as time goes on. X is getting smaller, y is getting bigger, c, well, depending on what point, it'll be getting smaller and then bigger. But here's my equation that relates the three together. And what I want to know is what's the rate of change of c. So we do this thing to this equation, which is take the derivative, which is this kind of like skill that we've been working on since probably late October.
I remember that word from high school, but I couldn't tell you what it
Yeah.
is. What's the derivative?
It's the rate of change. So if these two values are equal to each other, then if I find the rate of change of each side, those are also going to be equal to each other. So it's just a way of finding the rate of change of a function, and we have to use this thing called implicit differentiation because it's not like y equals stuff. When you have kind of like y mixed in with the x's,
Yeah.
we do this technique. And the actual differentiation process is going to be fairly simple. The exponent's 2, so when you have an x to an exponent, the 2 just kind of comes out in front. You leave that letter alone, and then you subtract 1 from the exponent, so it becomes 2x to the first. And then we got to add this x prime in there. It has something to do with the chain rule, but each part of it's going to be the same. 2y times the rate of change of y equals 2c times the rate of change of c. Once we get to that point, we actually do know we know what y is. Y is 600. We know x prime and y prime are given to us. We know x is 200. So we kind of know all this information. We're looking for c prime, the rate of change of this straight line distance. But we don't know what the c is yet, and that's a problem. We need to have everything except the one variable if we want to solve it. But that's where we can go into our Pythagorean theorem.
Okay.
The moment where the height is 600 and the width is 200, we can find out what c is using the Pythagorean theorem. So on the side, a squared plus b squared equals c squared. And in this situation, it's not a Pythagorean triple. The last example is when we can use like that 3, 4, 5 triangle again.
No, it doesn't work out this way.
It doesn't work out in this case. So let's see here. I don't like doing the mental math in my head.
36,000 and 40,000.
Well, yes.
No, I didn't get that.
So, yes.
No. 360,000?
I believe
And
40,000.
40,000?
And
Man, I haven't done math in a long time like this.
360,000. So we add those together.
So that's 400,000. And we want the square root of
And then, exactly.
400,000?
Exactly. So we're going to add these together and then take the square root of it. So what do we get? 400, what do we say, 400,000?
Mm-hmm.
So SQRT, if I just type SQRT in OneNote, it'll do it for me.
Yeah, squared.
Yeah, 400. 1, 2, 3, close parentheses. So it's about.
I was thinking it was 632.455.
You
You didn't ask. I didn't know that you wanted the answer in that moment. I thought we were building to it.
So I'm going to round to about 632 and a half, which is the hypotenuse at this moment, which makes sense. It should be bigger than 600.
So that's their distance when they start this problem.
Right, that's how far they are apart from each other.
Right.
All right, so now we can just plug stuff in and solve for C. This is a little bit of algebra, but before I do that, just a quick simplifying so the numbers are smaller. I'm seeing that I'm multiplying everything by 2 here, so if I divide both sides by 2, I'll just simplify it. The 2's will cancel out, and those 2's will cancel out with that too. So x is 200, so that is Jasmine's distance from the intersection, times the rate of change of x, which is 40, plus y, it's Theodore's distance, Teddy was just 600, times the rate of change, and his rate of change was negative 30, I believe it was feet per second. Now c we just found out is about 632 and a half, times the rate of change of c. So we could do a little, well actually some of this isn't so bad. 40 times 200, I think that's 8,000. 600 times 30, that's going to be negative 18,000.
Mm-hmm.
Equals 632.5 C prime. So 8,000 minus 18,000, that's going to be negative 10,000. So if I want to find what C prime is, just divide both sides by 632 and a half.
Man, math is cool.
It's all coming together. So The rate of change is whatever I get when I divide those numbers. So if I take negative 10,000 divided by 632.5, we get this. It's about negative 15.8, we'll say. And I think we're in feet per second here.
So
Yeah.
does that number mean that's how far apart they're getting how much further apart they're getting every second?
So at this particular moment, that is how fast this straight line distance is changing between them.
Yeah.
So at this moment in time, the distance is decreasing. Now, at different moments of time, the distance might be increasing or decreasing,
right.
depending on the speeds and at what kind of point they are from each other.
Yeah.
So it's not a linear.
But if they never change speeds, it would be the moment that he crosses the y-axis where their distance starts growing again.
Right.
That would be like the tightest it'll ever get.
Yeah.
Yeah.
So it's interesting how it's not kind of like intuitive. Like you might not have always expected that it's always negative or that it's positive.
No, yeah. No.
So at different points in time where these numbers are different, we might have different values here. But anyway, so that is one of the examples that we'll be doing in this section. And now we're going to move on to the next one.
Oh, okay. Shall I read it?
If you may.
All right. A 5 foot tall, oh, he's little. A 5 foot tall man walks away from a streetlight at a rate of 4 feet per second. The streetlight is 20 feet tall. At what rate is the length of his shadow changing?
All right, so we're trying to find out how fast the shadow is going in this case. Again, I like to start off by making a diagram and labeling the information that we have.
Is that a Sesame Street character?
It does look like a Sesame Street. You familiar with him?
No, actually I don't know the characters very well. It's not Elmo.
It's Blue Elmo to me.
Blue Elmo.
That's what I'd.
No,
Is it the Cookie? Not the Cookie Monster
No, not
either.
the Cookie Monster. Oh gosh, is there like a Groucho? No, that's a Marx Brother. There's someone like that. We'll look into this later.
Well,
take it away.
This is important. So we know that the height of the telephone pole is 20 feet. We know this gentleman here is 5 feet. So his distance from Grover with a G?
Grover. So let the record show I've gone onto my phone to look this up, and it's Grover, right?
That is him.
That's totally Grover.
Yeah.
Okay.
All right, so this is Grover here. Some Sesame Street thing came up in my life within the past 2 weeks. I can't remember what it was now, but it came up.
Really?
Yeah.
It's been a while since I thought about Sesame Street.
Something Elmo adjacent showed up. So the distance Elmo is from the street lamp, I'm just going to call that x. And the rate of change of x, so his speed right here, is 4 feet per second. So I'm going to call that the rate of change of x is 4. We're trying to find out what's the rate of change of the shadow. So in this case, this is the shadow. I'm going to use S for shadow. We want to know how fast that is changing, knowing how fast this person is going from the light. Now, whenever I make my S's, I put a little line through them. And it's for the longest time, if I use S's and 5s together, they start to look alike. So my S's, I try to do that to make them look different. Same with my 2s and my Z's.
Okay.
Now I have to do that to my Z's so they don't look like 2s after a while.
Yeah, I've seen that.
But I have an identity crisis with my Y's.
An identity crisis?
Like some days
well, they could be a 4. Is that what you're concerned about?
Well, some days I'm doing that.
Yeah.
And some days I'm doing that. Not only could it be a 4, but if I make a lot of Y's like that for a while, they're going to start to look like X's.
Yeah. And that's a mistake I make, actually. My Y's and X's look similar.
And then if I make a lot of Y's like this for a while, they could start to look like G's. And the problem is all these letters do get used a lot. And
yeah, which are pretty common letters in math.
And so some days my Y's are straight, and sometimes they're rounded, and sometimes they're both, depending on, I don't know, when I write my name Kyle, this is how I'm doing it.
Okay.
But that's like from my youth.
But in other circumstances, it's the other one.
Especially in math more so, I'm doing rounded Y's.
Yeah.
Anyways, so now we have this relationship between the sides of a triangle, and I want to find a relationship between X and S. And back in that beginning diagram, I was showing that if we have a nested triangle like this, they're going to be similar triangles. So the ratio of the height of this triangle and this triangle is going to be the same proportionality as the base of the giant triangle and the base of the smaller triangle. So the height is 20 to 5, so that ratio is going to be the same as the ratio from this the base of the triangle. The whole base is X plus S, because you got to put them together.
Right.
to the base of the smaller triangle, which is S. Now, 20 divided by 5 happens to be nice and 4, so we don't have to worry about fractions here.
Give me the easier ones from that one, please. If you have another 20 divided by 5 situation, ask your guest. That one I can do.
I got an easy one coming up here.
All right, cool.
To simplify this, because before I take the derivative, when you have a fraction, it can be a little bit more of a pain. So do a little bit of algebra here. I'm going to multiply both sides by s. So 4 times s is equal to x plus s. Now I have an s on both sides, so I'm just going to simplify it once more. And this is where you're coming in here. If I subtract 1s on both sides, 4s minus 1s is
3s.
There we go. So here is my relationship between the size of the shadow and the size of the distance from the, what's the name, Grover to the street light. Now I got to do that thing where I want to find the rate of change, so I take the derivative of both sides. And these are linear functions. It's just going to be 3 times the rate of change of s is equal to the rate of change of x. And I think we know one of these. We know the rate of change of x is 4. So 3 times the rate of change of s equals 4. And then we just have to divide both sides by 3 to find out what the rate of change of the shadow is. So at this moment in time, it's going to be 4 divided by 3, which we're just going to leave it as 4/3.
Fine.
But
it would be 3 1/3 though. No, 1 1/3.
1 1/3.
1 1/3.
Yeah, or like 1.3 forever or whatever.
Yeah, 1.3 forever.
Infinite. Yeah, that one goes on forever and ever. You know, when I was in high school, I thought it was the most impressive thing when a teacher knew what a fraction was as a decimal. Like one
they
half.
could just like convert it in their head.
They just they knew that 2/3 was 0.6 repeating, and I don't know. I never thought about it deeply enough to.
Well, now the students think you're impressive for the same reason. Doesn't that make you feel good?
It is like a surprising circle of things. Yeah.
Yeah.
And it's just because you have to spend more time doing it. But anyway, so the rate of change of the shadow is now 4/3 feet per second at that moment in time. And so I guess the idea here is setting up this proportionality is really where the tricky part comes up, because finding the relationship between x and s, once you do that, the actual algebra isn't terrible here compared to some of the other problems we've seen.
Mm-hmm.
But it's just setting up that relationship, and then this is called related rates because we're relating the rate of, in this case, x to s with some sort of relationship, and then we do this differentiation process.
Fun.
Yeah, so this last one is just a quick extension problem. At what rate is the tip of the shadow moving? So in this case, they just want to know how fast this whole distance is moving. You can kind of imagine that when you're standing really close to it, the length of the shadow it doesn't move very fast. But then as you get really far away, that shadow kind of shoots out a little bit quicker.
Right.
So it's not quite as linear as you might think. And the relationship is pretty straightforward. If we want to find the rate of change of A, we know this length is x and this length is s. So the relationship between the three is pretty simple. A is just whatever this x plus s is.
Mm-hmm.
So A, which is the tip of the shadow, is x plus s. So if I take the derivative of both sides, it's a simple derivative. The rate of change of A is just the rate of change of x plus the rate of change of s. All I did is put marks on it from your perspective, which is fine.
Yeah.
So we know the rate of change of x from the last problem is 4. We know the rate of change of the shadow is 4/3. So now we got 4 plus 4/3. And
Was I supposed to do that?
you can give it. I want to leave it as a fraction though, and I want to leave it as an improper fraction.
Is 5 1/3 improper?
That would be a mixed number. So something like 4/3 is acceptable, even though the denominator is bigger.
Mm-hmm. So is it 16/3?
Let's see. Yes.
All right.
Very good.
That's an improper fraction?
Yes.
Okay.
Improper. When the numerator is higher than the denominator, it's improper. In the young grades, they never write it like that.
Yeah.
And then all of a sudden you get to algebra and they say, that's how we're going to write
We want
fractions.
improper fractions.
Yeah.
Well, they shouldn't call it that if they want you to do it. That sounds like an incorrect thing. Like, oh, that's improper.
One of the things that I think gets algebra students the most angry is that at some point you work with what we call imaginary numbers.
I've heard of those.
And you can imagine how angry
Pun. Got it.
you can imagine how angry students get when you use the phrase.
They're not fans of imaginary numbers.
So I don't like the name of them because once you say imaginary numbers now, feels even more pointless.
Sure.
But they're a subset of what are called the complex numbers, and so I like to call them complex numbers instead of imaginary, just to avoid the word imaginary.
Okay.
Which we won't talk more about imaginary numbers, I guess, at this point.
I'm sure your students appreciate that.
All right, last example, and this is actually a classic example. I remember being in calculus, my teacher gave us a problem like this, and I was very lost when I was taking calculus. I wasn't a strong math student at that point in my life.
Same.
And my dad's friend at work has like a math degree from MIT, very highly ranked, and he brought it to his friend at work, and his friend had to use like some computer software to answer it. I go, that's not.
What?
And so he didn't know the kind of like the skills at the point in time, but also some of these problems, there's like especially in physics, like they'll give you an example that's like not realistic, like something that doesn't weigh anything, and we're not going to count friction as a thing.
Uh-huh.
So they call it the weightless monkey in a frictionless tube is what they say.
Yeah.
In these ideal situations, what would happen? But there's so many other things in the real world that would affect it.
Right.
We choose to ignore it, and I know a lot of these problems kind of have that ignoring part of it. But anyways,
This feels like the debate between Newtonian and Einsteinian physics. Am I right?
you'd have to fill me in. I'm not part
No,
of that.
we don't have the
debate.
time for that. All right.
All right, would you read this one
Oh,
for us?
happy to do it.
Yeah.
Okay. Jake leans a 25-foot ladder against his garage. After he climbs up, the ladder begins to slide down the side of the garage at a rate of 3 feet per second. That sounds dangerous.
Yes.
It's sliding down as he's on it?
Yes, not a good thing.
How quickly will Jake die? No. How quickly is the bottom of the ladder sliding away from the base of the garage when the top of the ladder is 20 feet above the ground?
All right. So in any calculus book in related rate section, you'll see this. You'll see the ladder sliding question for whatever reason. So we got a house, and we have a ladder on it. So let's see.
Can you please put a roof on that house so I know what it is? Appreciate it.
Of course.
Ooh, can you please put a chimney on that house
Of course.
so I know what it is? I appreciate that. Thank you.
You got it.
If smoke could be coming out of that chimney, so I understand what it is. Okay.
There we go.
Are there are no windows in this house?
That's fair.
It's just dark in there?
So as I'm creating this house, I learned most of my drawing from watching Blue's Clues.
I did not know that.
The guy would write.
Who was your guy? Who was the blues?
The OG guy.
Steve.
Steve.
Yeah.
So Steve would take out his handy dandy notebook and draw something.
Right.
And I just remember I'd watch him and then try to draw it myself.
That's cool.
And
now look at you.
well, ironic. So I heard that students learn to draw like diagrams and stuff from watching teachers drawing diagrams and stuff. But now because we just kind of like have diagrams like on the board, it's already like a perfect like picture of a house. We don't spend time drawing the stuff, so students don't see someone draw it. So now they're not as good at drawing it, and so it's like a skill that's decreasing is the ability to like sketch a diagram.
Oh, wow. Interesting.
Anyway, so we know it's a 25-foot ladder. Let's see. The ladder, we know that it begins to slide down at a rate of 3 feet per second. So this rate of change here is 3 feet per second. How quickly is the bottom of the ladder sliding away? So we're trying to find out how fast this is sliding away. When the ladder is 20 feet above the ground. So at some point in time, it's 20 feet above the ground. So I'm going to call this distance here x again. This distance down here y. And the hypotenuse we'll call c. I like to call it the hypotenutal.
Hypotenutal?
Yeah.
Is that just your thing, or is that like a thing?
Well, actually, it's Dobo's thing.
Dobo invented it?
Yeah, and I do like calling it the hypotenuse. So we know y equals 20, the rate of change of y. Now, because the ladder is sliding down, that distance is decreasing, so it's going to be -3.
Yeah.
We don't actually know what x is, but we can find it out later. And the rate of change of x is actually what we want to know. An important thing that wasn't in the last Pythagorean theorem problem is that the hypotenuse is 25, but no matter at what point when this thing slides down, does that change? The hypotenuse is always going to be 25.
Because the ladder is 25 feet.
Right.
Yeah.
And so this is a constant.
Constant.
And
the y is a negative number, just like when Theodore was driving toward Alamo Street, it's like going closer.
Right. So
Okay.
the distance, y represents a distance, and the rate of change of the distance is decreasing.
Yeah.
Now the height of the ladder is getting smaller and smaller, so that's not constant.
The height of, right, okay. How high Jake is not.
Right.
Yeah.
He's moving, and
Okay.
it matters when we do the derivative. So the relationship between x, y, and c is still the Pythagorean theorem: x squared plus y squared equals c squared. But like I said, c is a constant. I'm not going to use a variable. I'm actually just going to use 25 because that's never going to change. 25 squared happens to be a number, but we don't really need to know it when we do the derivative here.
Okay. 625.
Yes.
Yeah.
I didn't want to put you on the spot
No,
there.
I saw you make eye contact. I'm like, does he want me to say what it is?
I didn't want to put you on the spot
no,
there.
no, I
but
got that.
Now, did you just memorize that, or did you do something in your head?
At some point in my life, that one clicked for me. Yeah.
Yeah. Well,
I don't know what 24 squared is or anything.
Me-
But 25 is like a big one.
I can get up to 16.
256?
Yeah.
Okay.
And then 17, 18, 19, I don't have.
Then it falls apart.
20 and 25 are the next ones.
Right. 30s. Yeah. All the round numbers are fine.
Yeah.
Right.
Actually, that reminds me of a story. Maybe not. We'll talk about it at some point. If I forget later, it involves Lisa Simpson and an episode of The Simpsons.
Okay.
In math. But anyways, so now that I'm in a relationship, when I take the derivative of x squared is 2x times x prime, or the rate of change of x, plus 2y times the rate of change of y. Now the rate of change of a constant, the fact that it's constant means it is not changing, it is always 25, so the rate of change is 0.
Yeah.
So even though, it's 25 squared, 6 is 25, it's still a constant.
Yep.
Before I start plugging things in, I'm just going to divide by 2 on both sides, which just simplifies it so I don't have to use big numbers. So x prime plus y prime, 0 divided by 2 is still 0. And then I think I know x prime, we know is what we're looking for, so actually I don't know that. That's what I want to find. I know y is 20, y prime is negative 3. I don't actually know what x is yet. But here's where that Pythagorean triple comes up again.
Right.
So I have x, which I don't know. So if I did a squared plus b squared, the height is 20, and the hypotenuse is 25, we can figure out what x is. Now, I don't need to know that because I'm recognizing that this is a Pythagorean triple here. This is that 3, 4, 5
Right.
triangle, but scaled up a little bit.
Thinking 15, right?
It's exactly right. It's actually going to be 15. How did you get that?
225 plus 400 is 625.
Oh, so you just did the Pythagorean theorem.
Yeah.
Okay, so yeah.
Thanks to your lesson.
So it's perfect. So
Okay.
20 squared is 400 and 25 squared is 625. Subtract 400 on both sides, you got 225, and you square root that, you get 15. And the Pythagorean triple part that comes here is, I'm recognizing in my mind that 20 and 25, 20 is 4 times 5, and 25 is 5 times 5. So that if I did 3 times 5, that's my 3, 4, 5 triangle.
Right.
So 3 times 5 is also going to get you 15.
Oh, yeah.
And it's just one of those, it feels good when you recognize it.
Right.
But to do the actual arithmetic isn't really the worst thing ever either. At least in this case, the numbers weren't so bad.
It's good for your brain, too.
Yeah,
Get that practice in.
yeah, the reps.
The reps.
So x is 15, x prime is what we're trying to find out, which is the rate of change of x. Y we know is, I think, 20, and y prime is negative 3, equals 0. Let's see here, 20 times negative 3, negative 60. Add 60 to both sides. So 15 times something equals 60. That something is going to be 4. Yeah. So the rate of change of the ladder, I think we're in feet per second, is 4 feet per second. And it should make sense that it's positive because this distance as the ladder slides out is positive. So it should be the rate of change should be a positive number because it's getting bigger. But anyways,
Good stuff.
thanks for joining us.
Of course.
The people voted. Like I said, I had double-digit people voting on that poll.
Yeah.
You had overwhelming, I think it was like 80, it was either 88% or at one point, I don't know what it is at, once 10 people
An
voted.
electoral landslide?
And then the only other person that received votes was Pesca.
Oh, man. That's a tough competitor, too. I'm extra
Yeah.
proud now.
She was a little bit bitter, but she was happy that she got some votes when I talked to her about
Okay,
it.
good. I'll avoid her in the hallways
Yes,
anyway.
Taylor Swift got 0 votes,
Oh, so I beat Taylor.
and
That's huge.
Mr. Steady did not get any votes, but we won't tell him that. I
So
don't
Mr.
want him to
Steady
feel
and
bad.
Taylor Swift are like the same. They both got the same number of votes.
Yes, congruent.
Yeah.
Well, thanks. If you make sure you ring the bell for notifications, smash that like button if you liked it. This video was brought to you by
You have a sponsor?
no, but I like to end it with this Moe's.
Oh, yeah, Moe's.
Welcome to Moe's.
Did you go to Moe's last night?
I go on Wednesdays now.
Okay.
If you go on, it's on
And
the
I'm
app.
a Tuesdays guy now.
Really?
Yeah, my schedule changed. But for those at home, you and I used to go to Moe's on Mondays. Coincidentally, we'd bump into each other
Correct.
because they had like a Moe's Monday deal.
Yeah.
But you're not a Monday guy anymore. You're a Wednesday guy, and I'm a
Right.
Tuesday guy.
Yeah. That is how we bonded.
Yeah.
That is how we
And now look
bonded.
at us.
All right. Take care.